Well, thank you. So in case you don't recognize this thing, this is the infamous galaxy NGC 1275. It's the central galaxy of the Perseus cluster. And the big H alpha nebulae here has long been known, and it was considered decades ago, it was called an exploding galaxy. Maybe that's not such a bad way to describe it now. But the thing I wanted to point out about it is this is a massive elliptical galaxy, and massive elliptical galaxies have the reputation for not having any star formation. But this thing has star formation. It has multi-phase gas. And you can even see star formation happening out here. And these filaments of gas extend tens of kiloparsecs away from. And so this is an example of a phenomenon that we've come to call precipitation. And I want to make a few big picture points about it in this talk. One is galaxy evolution, whether galaxy forms stars or not, how quickly it's forming stars. It turns out to depend a lot on the circumgalactic gas around it. And while this situation is obviously very complex, I think what we're finding is feedback, while it's complex, has some rather simple, surprisingly simple emergent behaviors that help you understand it in a more general way. And one of them is precipitation, which I'll try to convince you is a natural regulator of star formation in these massive galaxies, and maybe galaxies like the Milky Way also. So in this picture, you're seeing optical emission from the stars. You're seeing optical emission, H-alpha emission here. If we turn up the X-rays a little bit, you can see X-ray emission from the hot gas surrounding the galaxy in the cluster. If you now take this and you do some digital unsharp masking to bring out the features, you can see this. So you can see a whole lot of wave action around this thing. So this is highly enhanced. The details are probably artifacts, but the major features are sound waves and gravity waves that are propagating around the circumgalactic medium. A lot of them are generated by the active galactic nucleus at the center that keeps pumping out energy into its surroundings. I plan on saying a few things about those waves at lunch, and I won't talk about it anymore here, but I want you to remember that picture. Okay, so as was said, I was an undergraduate here, so if you'll indulge me for a minute, yeah, I will. Yeah, so I ran track here, and I won some Ivy League championships. Thank you very much. Yeah, thank you. Yeah, yes, this is Harvard. Beating Harvard is good. And I got a degree in 1983 here. And to do that, I had to do a senior thesis. I did it with Ed Jenkins. And in putting this talk together, I realized that my senior thesis is related to this talk. Here's the cover page. It was measuring interstellar gas, the fine structural lines of carbon, to try to assess the pressures of interstellar clouds in the Milky Way. And the reason that has relevance has to do with this gentleman, who I'm sure some of you recognize. You might recognize him better. He looked more like this when I knew him. This is Lyman Spitzer. And Lyman Spitzer, in 1956, wrote a really remarkable paper. He had just learned about the pressures of interstellar clouds that were out of the plane. In fact, Ed told me yesterday that observation would not be published until 5 years after this paper was published. But in knowing that there were clouds of significant pressure, and these are 100-degree clouds, and you measure the densities and you can infer pressure, because these clouds existed and they weren't just in the center of the disk, he said, there must be a confining medium. And if I know the pressure of the clouds, I could calculate the pressure of that medium. And if it has a temperature similar to the virial temperature of the galaxy, and the galactic rotation speed was known, I could infer something about a gas that might be confining at all. And he called it the interstellar galactic corona. And once you know that, you can make some calculations. So here's temperature of 10 to the 6 degrees, electron density. And you can calculate the rate of cooling rate. And he calculated that the rate of cooling, that this gas could lose its thermal energy in 10 to the 9 years. In other words, less than the age of the universe. And so many decades later, people started worrying about overcooling problems in galaxy formation. But as far as I can tell, this is the first time it ever showed up. The fact that there's gas around a galaxy that can cool in less than Hubble time. And so he speculated, Condensation of cool matter from the corona may perhaps account for formation of new spiral arms as the old ones dissipate. Here's a calculation. In order to get this result, he had to say, well, the cooling is not just free. There's also emission lines from high ionized species, but he happened to know a few things about hot plasmas and was able to calculate at 10 to the 6 degrees. He estimated a cooling time of about a gig a year and said, you know, this could tentatively be identified as the source of material for the spiral arms, condensing and maybe giving you thermal instability. And it is very apropos of 2017 to be talking about these things, and he was talking about 1956. So when I think about circumgalactic gas, it is usually customary for people to talk in terms of density and temperature, because those are concepts we gravitate towards as humans. But I think it's deeper to think about what's going on in terms of pressure and entropy, where entropy here is quantified as the constant of proportionality in this equation of state. It's specifying the adiabat that gas is on. And so if you know the density and temperature, or equivalently the pressure and the entropy, you can calculate a cooling time for the gas. And entropy in these units is an energy divided by a density of 2/3 power, and so it has units of keV centimeters squared. And these lines here are lines of constant cooling time. Now what's useful about looking at things this way is the vertical, or the horizontal, is like what hydrodynamics does. You can move gas around adiabatically and it'll change density and temperature, but the entropy stays the same. Whereas the other direction, the orthogonal direction, is the direction of thermodynamics. To change the entropy, you have to radiatively cool, or you have to dissipate energy as heat energy. And so if you're looking at density and temperature, you can get confused about what's really cooling and what's not cooling. For example, in star formation, the center of the star gets hot because of radiative cooling. It's in a gravitational potential. And so temperature is not telling you everything you need to know about where the energy is going. Okay? And so this is a handy way to look at it. Now, one thing I want you to notice here is adiabatic processes in this temperature range don't change the cooling time very much. Right? If you're on a certain adiabat and your temperature is between about 3 times 10 to the 5th and 3 times 10 to the 7th, and you're moving the gas to different pressures, you're not changing the cooling time that much. And that has the effect that, right, you can, if you shock gas, once you shock it above about 10 to the 5th degrees, you're raising the cooling time. You're making it harder to cool. You're adding entropy to it. And this is what cosmological structure formation does. It's where all that circumgalactic gas gets a lot of its entropy. When it can radiatively cool, it tends to sink and get compressed and stay about the same temperature, even though it's losing energy. Okay? So if you cool, you will continue to go to lower entropy, but unless things go multi-phase, you're going to stay at about the same temperature. All right, and so here's Spitzer in 1956. If you do the same calculation today, he wasn't very far off. The cooling time may be a little shorter than he calculated because there are more transitions that you can put into your code, but it wasn't a bad estimate. The takeaway from this, I'll quote from his paper: the problem of origin of such a corona reduces permanently the problem of heating. And that's as true in 2017 as it was in 1956. Question?
So in 1956, the value of the Hubble constant, therefore, the age of the universe was very different.
Well, okay. I don't think he said much about that in this paper.
But in terms of just asking, is 10 to the 9th year a long time or a short time?
What he says is he can say it is unlikely to be primordial. Now, whether he thought, how old he thought the universe wasn't stated in the paper, but it's unlikely. Maybe stellar ages were already established to be more than that, but yeah. Okay, so we don't really call it a corona so much anymore. Now we call it the CGM, circumgalactic medium. And if you were sitting down to write a textbook, say 20 years ago, you might have put in a diagram like this, pointing to the basic parts of a galaxy. But in the intervening time, it's become essential to add this part. Scott Tremaine, among others, has drawn a lot of attention to the fact that the central black hole seems to be a very important component of the galaxy and may play a big role in galaxy evolution. And when you're sitting down to maybe revise a textbook in 2017, it becomes really important to now talk about the circumgalactic medium. because when you do absorption line studies of lines of sight through two quasars that go through the halos of galaxies, you find absorption lines indicating there's lots of mass out there, at least as many baryons as there are in stars in the galaxy, and at least as many metals as there are in stars in the galaxy. So much of what the stars have made is out there, and most of the gas associated with that halo of dark matter is out in the circumgalactic medium. And so we've largely ignored it because it's so hard to see, but sometimes I think of it as the yolk. It's like if you're trying to understand an egg without looking only at the yolk, you're not going to understand an egg. I think it's a similar case with galaxies. Okay. So here now is a massive elliptical galaxy where there's not much star formation happening. And it's long been known from radio observations that they're often bipolar jets. And from the radio morphology, it's clearly running into something. Okay. And with an X-ray telescope, you can see the something. So there you go. So there's hot gas out there. The galaxy, the galaxy's central black hole is clearly interacting with it. And the thing that has been really puzzling to understand is somehow this looks like a finely tuned system. The black hole down at less than a parsec seems to know how much energy to put out to regulate the radiative losses in a region with a radius of tens of kiloparsecs. How does that possibly work? Just to make that a little more quantitative, here's our diagram again. Well, that's the Andromeda galaxy. NASA has not yet provided us a picture of the Milky Way from out in the halo. But these estimates are from models of oxygen 8 emission lines, oxygen 7 emission lines by Miller and Bregman. And cooling time gets larger as you go out, but that is a complementary measure to what Spitzer was arguing. And 10 kiloparsecs, roughly, you're about a gig a year. Okay? And if you look at a massive elliptical galaxy like NGC 4472, it's quite a bit hotter. With the X-ray observations, you can estimate cooling times. And interestingly, at 10 kiloparsecs, the cooling time is about a gig a year. Also, right in close to the center, the cooling times get shorter and shorter and shorter, right? And it's not condensing so much and forming stars so much. You need pretty tight regulation to get this to happen. Okay? Let's go to M87. It's now at the center of run-of-the-mill galaxy cluster. At 10 kiloparsecs, the cooling time is about a gig a year. And HC 1275, the cooling time at maybe 20 kiloparsecs is about a gig a year. Okay? So there's a wide range of pressure in here. These systems are all somehow regulated by feedback. And yet, if you ask, where's the cooling time equal to about a gig a year or a few gig years, it's in the 10 kiloparsec to tens of kiloparsecs region. And so sometimes people worrying about star formation quenching in galaxies, just the word quenching, for many years, people have pointed to mergers of galaxies as having a big role. You have a merger, you have a starburst, you use up all the molecular gas, and then you're quenched forevermore. But in fact, when you look at a massive elliptical galaxy, there's plenty of gas around that can cool in a short period of time. And that means if for a galaxy to remain without star formation for a long period of time, it has to be a steady state of the circumgalactic medium and not a single event. And I think this is, in some of the conferences I go to, this is a huge misconception, that quenching is something that happens, then you're done. Okay? It's a CGM steady state that we have to understand. Now, okay, there are plenty of decades worth of papers on thermal instability and condensation. And I'm feeling giddy because it's like old-timey physics, and yet the behavior is so rich and the literature is so confusing if you go through it. I want to point out some kind of simple concepts that emerge that need to be respected, I guess. Yeah. So the first thing, before I get to the concepts, this is like the fundamental hypothesis of the whole talk, and it's very general. And if you now have a hot medium, you can calculate what's the bonding accretion rate on the central black hole. And it's some number. But as soon as it starts to condense and you make cold gas, the bonding accretion rate associated with the cold gas is much, much faster. Okay? So if you can cause a phase transition that turns the hot gas into cold clouds, you can supercharge AGN feedback. There's still angular momentum issues to solve. But it suggests that a transition from a single phase to a multi-phase medium can dramatically ramp up the AGN accretion, the feedback that you get. If that energy is effectively transferred to the surrounding medium in a way that would lift the instability, lift condensation, then you're very naturally going to have a system that tunes itself to a state where it's marginally. It's like a transition edge sensor or something, right? If you have a transition to a multi-phase medium that quickly ramps up feedback and puts thermal energy back in, it's going to naturally regulate into this marginally precipitating state. And the fundamental argument of the whole talk is this is happening in galaxy clusters. We can show that it is. I'll show you evidence. And it may be happening much farther down the mass spectrum of galaxies. Okay. In order to understand how that works, we need to talk about cooling times and free fall times. I think this goes back to Hoyle 1953, maybe earlier. In order to know whether you go from a single phase to multi-phase medium, you're trying to understand whether a perturbation can develop contrast. And if I have a slightly denser blob here, it's going to sink. And if it's sinking to a region of higher density, I have to understand whether it can remain, a high if it grows in contrast or not. And to understand that, I have to compare the cooling time, the rate at which it's losing entropy, to the rate in which it's going to accelerate downward. Here is an example of simulations that have been done by a bunch of people recently, where you look at condensation in a medium that's forced to have heating equal cooling on each equipotential layer. And so this is a plane parallel arrangement, where the thing that changes between the panels is the ratio of cooling time to free fall time. If cooling time is short, well, sorry about that. If cooling time is short compared to the free fall time over here, you basically have clouds that are cooling in place. They condense before they can fall. If the cooling time is fast, or is slow compared to the free fall time, what you have are things that sink, and they don't develop much contrast before they merge. They reach a layer of similar entropy, and not much contrast develops, except here near the midplane, where the free fall time becomes singular and gravity is not doing what it should do. Okay. And then if these time scales are roughly equal, you get this lava lamp effect, which I could stare at for hours. And I won't tell you what we've consumed while staring at that. But, the point is, this ratio is a very important dimensionless number in the dynamics. The other thing that matters is what the entropy gradient is. And so this was part of the literature in cluster cooling flows going back to 1980, Len Cowie et al. And it's a concept that I think is underappreciated, which is if you have an entropy gradient, then and this ratio is large, then as you sink, your contrast is going to decrease, and you end up having oscillations, which are essentially internal gravity waves. Okay, this is just a gravity wave, and if the gravity loses energy, these oscillations will die, and you won't get condensation. Whereas over here, if the entropy gradient is 0, that blob is going to lose entropy, and its contrast is going to grow. And so that situation leads to condensation. And so one of the important features of a system, whether it can condense or not, has to do with what the large-scale entropy gradient is. Okay. And we've called that buoyancy damping in a recent paper, because it didn't have a name before. Now here's an example. Here's a simulation where another concept comes in. This simulation happens to be by Lee and Bryan, but Massimo Gaspari has done other simulations like this, where you start with a homogeneous gas at a temperature of a few times 10 to the 7, a galaxy cluster type potential. And there's something called a black hole here, which the function of this so-called black hole is if you have accretion onto it, it produces bipolar outflows. Okay? And well, first I'll just show you what happens. So it starts homogeneous, and then you feed the black hole, and then you're getting condensation along the axis. Okay? So you went from a situation where the medium was homogeneous to now a multi-phase medium. And the reason that happens in a medium where the cooling time to free fall time ratio is long is because of uplift. And the analogy I like to attach to this is a thunderstorm. Right? If you have humid gas and you lift it up, it cools adiabatically, you hit the dew point, and you get condensates that then rain back down. And that's analogous to what's happening here. when the outflow starts from the AGN, you're lifting up lower entropy gas from the center. As it goes up, it starts to condense, and then you can start temporarily adding more fuel to the black hole because you're making this process supercharged. If you let it go on a little while, there's phase mixing. The whole thing gets more randomized. But all this stuff was spewed out here because of uplift, and now it's spread over a region tens of kiloparsecs in size.
So you put in by hand the feedback on a black hole.
Right. Well, what you say is, I'm not going to resolve all the way down to the Schwarzschild radius, right? What you're saying is, at some pre-specified radius, if cold clouds cross that, then I'm going to put energy back in, and I'm going to put it back in a combination of kinetic and thermal form. Okay. Right. These are HST UV pictures of the central galaxies of some famous galaxy clusters. And if I were showing these to you and said, these are highly star-forming merger galaxies at redshift 2, you'd probably buy it. Right? But these are not mergers. Okay? These are the central galaxies of clusters. And often, this star formation is aligned along the outflow axis. Okay? So people have puzzled over this for a while, like decades. Where is this gas coming from? Early on, people said, oh, it must be condensing directly out of the intercluster medium. Okay? But one of the curious things about that, and I had a long talk with Bruce Drain about this, is there's molecular dusty gas here. Okay? And the gas around it is not molecular, is not dusty. So there has to be some connection. Pardon? Yeah. So often it's correlated. Yeah. Yeah. Okay. And so in at least some of these systems, well, yeah, the central galaxy is implicated. And what the emerging tail is, as we look more and more at this, there's actually molecular gas that is flowing, at highest speeds right along the jet axis. Okay. And I don't think the jet's pushing on molecular gas. It's very hard to push on molecular gas with, it's like trying to blow boulders around with your breath, right? But I think what's much more likely is you're inducing condensation to happen because of this uplift process, precipitation. All right. Yeah. And so then what conditions are necessary for that to happen? You can ask the question, if I now lift gas up, when do I get it to condense? And I'm going to remind you of this plot. When you're lifting it up, it's going to lower pressure, but the cooling time isn't changing that much. What's changing is the free fall time. So if you're starting at a ratio of maybe several times the free fall, cooling time to free fall time is a few, you only have to lift it up a couple times the radius before the ratio of that blob is now 1, and it can condense. And so this plot here is just showing very simple calculation, assuming ballistic trajectories. They're probably not ballistic, but this gives you some scaling. And you can ask, if at the base of the flow, you have a certain ratio, and I uplift it a certain ballistic, shoot it up in a ballistic trajectory, can it cool before it comes back down? And the answer is, if you start out with a ratio of a few times the free fall time, and a modest outflow velocity, you're going to tend to make more fuel. Okay, so anything in this regime is likely to be very volatile to having an AGN going off the center. Once it goes off, you're actually going to have a positive feedback process for a little while because uplift is just going to generate more fuel. But if that process gradually adds heat to the system, you're going to raise the cooling time. And if it gets up here, even if you uplift now 2 times the circular velocity, which is chosen because it's hard to get thermally driven outflows that go out faster than that, once you get above 20, it's very difficult for uplift to now cause the gas to condense. It'll fall back down and come back to its region of similar entropy before it actually condenses. Okay? And so you get this general statement that at least when uplift's involved, you don't need crazy uplift velocities to get condensation even when this ratio is about 10. So I might talk about turbulence later. So if you're going to now quench a galaxy with some feedback from a black hole, there are a few things you have to manage. The cooling time to free fall time ratio matters. The entropy gradient matters. And uplift matters. Okay, so these are the basic components now of a system that has the potential to be self-regulating.
Can you go back just 1 second? So
Sure.
you were saying that the cooling time is not changing.
Yeah.
So if the cooling time is not changing, it doesn't really matter whether you lift it up or not. It's going to cool in the
Okay. So if you are in global thermal balance and you have an entropy gradient, you're technically thermally unstable in a linear regime. So gravity waves will grow, but they don't grow to condensing amplitudes. Instead, they shed their energy to sound waves and saturate. Okay? So if you have a heating mechanism that the time average balances cooling, you don't necessarily get a multi-phase medium. There are other conditions that have to be satisfied. One can be that you flatten the entropy gradient, and then this damping mechanism doesn't work anymore. That's one way. You can make the cooling time less than the free fall time, and it can just condense out without buoyancy mattering. Or you can do uplift. So it doesn't just naturally become multi-phase without one of those things happening if this is your ratio. And this is because you're assuming some sort of time average thermal balance. Okay, and so that's the key feature.
Now, if the disk is rotating,
Yes.
and then you lift up the rotation, the gravity is function height.
Yep.
So things mix up.
Yeah. So rotation is a complication that I'm not going to address. And in a way, we've been getting these results that I'll be showing without considering much rotation. You can talk to the person next to you about what happens when rotation enters. I don't want to. We can spend time in the Q&A. It's interesting in and of itself, but the world expert in that is there.
Can you go in the harmonic oscillator? Can it oscillate back up and down?
I'll be talking about that at lunch. If I can. Yeah, I mean, it turns out, yeah, lunch preview, right? It turns out, considering this behavior as a simple harmonic oscillator, that then you start to consider the nonlinear effects, I find very interesting. There's your ad later. See lunch later. So ask me again later. Yeah. What I want to get to is, yeah, where are you here? I gotta go. Yeah, why you should be listening to me to say this at all. That's always good, right? And right. Yeah, what's the evidence that this actually happens? Okay. So the thing, yeah, these are two central galaxies of galaxy clusters. One is obviously very multi-phase. It's the central galaxy of the Perseus cluster. The other is famously single-phase Coma cluster. And if you survey the central galaxies of massive clusters, you find that it's roughly half and half. Some have multi-phase gas, others don't. If you take the Chandra archive and look at all the X-ray data you can and say, how is the multi-phase nature, how does that relate to the ambient gas? What you get is a plot that looks like this. And so this is like pillar one of the evidence that this ratio of 10 is something of broad importance in galaxy evolution. These colored lines, the brown line is the cooling time profile you would get from just cosmological structure formation. You have shocks, you generate entropy, you get a profile, and if all you had was shot gas that could never radiatively cool, you'd have halos that would fill up with gas that, if you calculated a cooling time, would look like this. And at large radii, that's what clusters converge to, whether they have multi-phase gas or not. That's the cosmological part of the cluster. But on the inside, you can see that the things that have short cooling times have a very distinct lower envelope. And so this line is the line along which the cooling time would be 10 times the free fall time, where you calculate the free fall time by saying, well, you have a large cosmological halo with an NFW profile, and a galaxy, a central galaxy that's a singular isothermal sphere at the center. And so that's the only elements that go into calculating this, this magenta line, and it just tracks the bottom envelope of those profiles. It looks like there's a limit below which these things can't go. And the hypothesis here is that's the lower limit of a precipitation cycle. That you can't, if you try to get the gas to go to too low a cooling time, it becomes volatile, and the AGN will just push it back. Whereas these things over here, once you have heated it above a certain amount, which in entropy terms is 30 keV centimeters squared, then the cooling time is about a gig a year, and other processes can become competitive. They may include conduction, they may include dynamical heating, but once you raise the cooling time enough, other heating processes become competitive, and these things get lifted further. So it looks like there's a very distinct bifurcation. So this is quite striking, because it says whether or not you have star formation in these galaxies depends entirely on the state of the ambient circumgalactic medium. And so you have this, this floor. So the next question you might naturally ask is, what about massive elliptical galaxies? And they turn out to come in two types also. Some have multi-phase gas. Neither of these have much star formation, but some do have extended nebulosity, including molecular gas out beyond a kiloparsec, whereas others don't. And if you ask the same question about them, you get figures that look like this. These are some famous nearby massive ellipticals in which you can get very good Chandra data. These data from Norbert Werner. And when we analyzed it, we found if something has extended multi-phase gas, in the 1 to 10 kiloparsec region, it tends to just track this constant cooling time over free fall time ratio with a floor around 10. 4 of these 5, well, certainly all of them outside of a kiloparsec, stay above 20. And this rise here is consistent with supernova 1A heating, actually. Curiously, there's one of these things that has a lower ratio inside a kiloparsec, and people who know their way around nearby elliptical galaxies. This is NGC 4261, and all of them have active galactic nuclei, but the power coming out of this one is 100 times more than the others, and it has a dusty disk right down within about 100 parsecs. So one example like this isn't a proof. We're working on more. The trick is getting really good X-ray data of high resolution and good signal to noise. It's challenging. But it's very interesting to see that over 2 orders of magnitude now in radius in this sample, the ratio 10 still shows up. Given that you can't get fantastic data on everything, you can use a cruder test. And so here, what you can do is you can say, well, suppose this is true. Cooling time over free fall time is just regulated to be no lower than 10. That becomes an upper limit on the density profile as a function of radius. And so the free fall time here is a function of radius. These two things are functions of temperature. And if you have this expression, you can integrate to say, what kind of X-ray luminosity do I expect to be coming out from within a given radius? And to make things simple, you say, well, just assume temperatures, it's isothermal gas, it's an isothermal potential, and you end up with this approximation. So you're saying the luminosity prediction from within a given radius is this function of temperature, and the novelty here is that this cooling function ends up in the denominator. Usually when you are doing calculations of how much X-ray emissions something has, the cooling function is the numerator, because it's specifying how efficiently the gas can cool. But because of this limit that feedback sets, hypothetically, the cooling function ends up in the denominator. If you make it the gas, if you say the gas is now, simply add elements to it that make it easier for the gas to radiate, then feedback has to push it to a lower density in order for this to be true. Okay? And so you square that, and you get it into the denominator. So you get a complicated function here of temperature. And now, and so here now is this limiting prediction on this axis and luminosity everything radius on that axis. This is the data I've been showing on galaxy clusters. The blue points are the ones that are multi-phase, the red ones are not. And these tracks are as you start opening up the radius, you are including more and more luminosity. And so at low radius, you have lines that graze the limit. And then when you get to the cosmological parts of the cluster, it diverges. Whereas the things without multi-phase gas, they don't come in here. They're more like that. Okay?
Now, the Hubble time over free fall time
Yes.
happens to be at 10 as well.
Well, this is as a function of radius now. This is can go from very small free fall times, 10 to the 7, 10 to 6 years at the very center. And so all those time scales are getting shorter. So the Hubble time doesn't matter until you get far out. Okay. How far in practice? I'll get to that question in a few slides because it depends on what kind of halo mass you're looking at. Okay. If you go down a little bit in mass, you can look at a sample of groups. And again, here's the limit. You can collect data from a much larger sample of 1 keV type objects. It includes central galaxies of groups and massive ellipticals. And this is the inner, kind of the inner profiles do this. And I recently, this is now the ellipticals I was showing you earlier. It's small radii. Whoops. Uh-oh. Okay, I'll just. For the well-resolved ellipticals, you can get tracks that come and graze the line, like I showed you in that other plot. The whole host of points that appeared came from a collaboration that includes some local people, Andy Goulding and Jenny Green, who did a large X-ray archival survey of both the massive survey and the Atlas 3D galaxies. So those are volume-limited local samples of early-type galaxies, where what I really liked about their analysis is they took a controlled approach to the aperture. They said, let's just use an aperture that's the effective radius of the galaxy and say how much X-ray emission is coming out from there. You can then plot those points up. And as a whole, they continue to adhere to this limit. You can also ask, do those galaxies contain extended multi-phase gas? When you have CO detections, these red dots mark the CO detections. If you have optical emission line nebulosity, there's a cyan symbol on it. And there's not as distinct a bifurcation, but you don't have high resolution measurements of cooling time to free fall time ratio anyway. The point is, the closer these early type galaxies are to the limit, the more likely they are to have multi-phase gas in them. And then you can also add the Milky Way. So these tracks are from the Miller and Bregman modeling of oxygen 7 and oxygen 8 emission. That star is 8 kiloparsecs. So this is, this is now the X-ray luminosity that Lyman Spitzer could have inferred in 1956. Okay. And over 7 orders of magnitude in X-ray luminosity, this complicated function of temperature ends up giving a very straight line. Okay. You might expect there to be temperature structure in this prediction, but there's not. And so this appears to be quite a firm upper limit on luminosity and on density, and it comes from this very simple principle.
Just to further understand,
Yeah.
this is just saying that line corresponds to cooling time is 10 times the free fall time.
Yes. Yes.
So it's basically saying if your density is higher than that and the cooling time is
Yeah.
shorter, then you just condense out.
Right. Yeah. It's saying, that at that limit, there's something that doesn't allow you probably have condensation, and feedback will prevent you from going to higher density. Yeah. Talking about the ambient medium. Yeah. The ambient medium goes to higher density. Condensation will fuel feedback that heats the gas back up and pushes it to lower density. That's the statement.
Well, it's not necessarily creating feedback. It could just be condensing out, and then you don't see it as X-ray emission.
Well, if you get too much to condense out, then you have lots of multi-phase gas, lots of cool gas and star formation, which isn't seen.
You said you didn't have much star formation.
I guess what I'm saying is the fact that you don't have much star formation says it's not all just condensing and dropping out, because then you'd have this large accumulation of cold gas, much larger than you see. Again, it's another form of the cooling flow problem. So something has to be pushing back. Okay. Yeah. If you now look, this is kind of now getting to Michael's question. This is now asking about X-ray luminosity within a cosmological radius. Okay, so R500, which is the radius containing 500 times the critical density, okay, is a commonly used thing in X-ray astronomy because galaxy clusters are well observed out to that radius. It's also the radius out to which hydrostatic equilibrium is okay. When you start getting much beyond that, you get into these regions where the cosmological inflow is getting thermalized. And so, it's long been known that, if all these objects across this whole temperature range were just purely cosmological structure formation, the luminosity temperature relation for them would look something like this. This is saying, you know, all objects are self-similar in the circumgalactic medium. And it's long been known that this doesn't hold, and that feedback somehow suppresses the star formation, right? If you're a galaxy cluster and you ask, where does precipitation limit you relative to cosmological, it's a pretty small region at the center. It's about 30 kiloparsecs compared to, you know, a megaparsec. If you ask about a group of galaxies, the region subject to precipitation is larger and the Vira radius is smaller. And so, in a way, the luminosity that you would be getting from this region is suppressed. And so these models are showing if you meddle with the limiting cooling time to free fall time ratio, you're now starting to push down the extra luminosity from the center. If you go to something that's the scale of the Milky Way or a little bigger, the whole thing within R500 is precipitation limited. So that's the answer to your question. Okay. If you look at galaxy clusters and groups out to R500, these are a few different samples, and it's probably no surprise that they are following this predicted relation pretty well. And if you fit those relations, you get these lines that continue to extend down to galaxy scales. Something I found quite interesting was work that Massimo participated in, Anderson et al., where what they did is they took a large sample of luminous galaxies from Sloan, like 250,000, and they took cutouts from the Roskilde Sky Survey and stacked them up to see how much extra luminosity you're getting from galaxies of that type inside R500. And so here are the answers. And no surprise, galaxy clusters are like galaxy clusters. But below where you can do this for individual galaxies, the relation continues on down. And if you put the Milky Way on here, this is 100 kiloparsecs out in the Milky Way. And even the Milky Way seems to adhere to this relation. OK, so this is with a very simple statement. It seems to account for the luminosity temperature relation over 3 orders of magnitude in halo mass. Okay. So this seems to be a principle, and we don't know how far it's extending, but it's a principle that goes pretty far down.
When you talk about free fall time, physically, what is that? I mean, is there a sonic time also? Or?
Well, in a way, when I say free fall time, the way it's defined here is saying, you take the radius and you divide it by the 1D velocity dispersion you would get from stars in isothermal potential. Or another way is radius divided by circular velocity, whole thing times √2. You know, that kind of thing. And it's so it's like a clock. You know, whatever dynamical processes are, that's the clock speed. And so, yeah. Now, how does this work in simulations? This might not be, I know, Max has a lot of great papers on this. This is one of my favorite diagrams. I don't know if it's his. But this is the figure that convinced me that simulations could be convincingly self-regulating without fine-tuning. This is a simulation where there was bipolar feedback, kinetic feedback, that was fueled by condensation. And it started at kind of a lowish cooling time to free fall time ratio, and it clearly finds a self-regulated state. Okay. To show a picture, a movie of that, here's one from Yuan Li, where now you're seeing a 300 kiloparsec region. Oh, the music's playing. Do people want the music? Is that good? I know. It's very graceful. I'll leave it on. I swear I turned the volume off. Okay. But what you see is kind of a feedback cycle where gas is condensing, fueling the black hole. In this simulation, it is eaten up by star formation. So there are temporary periods where it goes away. But then it goes away. And then, without a feedback source, the hot gas has to go back into a precipitating state. Okay. And so this just keeps repeating. And here's a graph of what the total cold gas is like compared to the minimum cooling time to free fall time ratio. And except for a few episodes, it's self-regulating in the range very similar to what's observed. I want to go in just a little more detail about that because it's kind of cool to see the principles that I've been referring to play out in this simulation. So this is the same simulation, but now you're looking at entropy as a function of radius, and it's going to be an entropy distribution plot. I've drawn on the line where the cooling time is roughly 10 times the free fall time, and so this thing starts in a homogeneous state at all radii. But it's right at the point where in the center it's about to trigger the AGN. Okay? And so in a matter of 100 gigayears, now you're in a state like this. Okay? So that's the leading edge of the bipolar alpha, high entropy gas coming out from the center. And here you're having uplifted low entropy gas condensing out. So this didn't cool from here. It was actually pulled out because gas here couldn't cool possibly that fast. Then, over another short period of time, you've either pulled out or condensed all the low entropy gas in the center, and the profile is starting to flatten out. There, because the entropy gradient is flat, you're not damping condensation anymore. But out here, as you watch, you'll see buoyancy erasing the entropy inhomogeneities. So you can see damping there, but inside here, you get kind of a continually a very multi-phase medium until this gas is exhausted. And what you'll see in the next snippet is this stuff is going to become more homogeneous, and the instability in condensation is going to grow nonlinear here. Okay, and there it goes. And then over another short period of time, it achieves another long-lasting self-regulated state. Okay, and so this system is self-regulating because of the interplay between the local and the global. When you set off an agent at the center, you tend to overturn the entropy gradient. That temporarily produces more fuel. But farther out, if you can heat and maintain an entropy gradient out here, you don't get much condensation on the outside. So whether or not your condensation happens because you're regulating the large scale, well, the feedback processes are regulating the large scale entropy gradient to control whether the gases can go multi-phase or not. I'm starting to run low on time. I'm trying to decide how much stuff to cut from the end. I do want to show this because it gets at implementations of feedback processes, some of which can be self-regulating, some can't. This is from my thesis student, Greg Meese. And they're 6 realizations of the same basic setup, except in this one, there's no kinetic feedback. It's all thermal energy put at the center. Whereas in the other 5, there's various ratios of the division between kinetic and thermal energy. And you can see that 5 of them are self-regulating, and this one isn't. The reason it isn't is because if you put all the thermal energy at the center, you naturally make convection, you raise the entropy gradient, and you make it thermally unstable. Okay? The vast majority of simulations called AGN feedback are central thermal energy that can't stop the condensation process unless they raise the cooling time a whole lot. Right? It's not the way it works, and it doesn't self-regulate. Okay? The point of the kinetic feedback isn't that it's kinetic, it's that it distributes the energy in such a way that doesn't overturn the entropy gradient. And that's the key to getting quenching to happen, I think. Okay. Let's see. What other points do I want to make? I won't have time to do all this. But the point I wanted to make here is that there is the prevailing view of what regulates star formation in galaxies is that lots of stuff comes in cosmologically, gas enters the galaxy, and then a wind blows out most of it. And so in that picture, the regulation has to happen here with lots of what's called mass loading. In the precipitation picture, it's highly complementary. In a way, you're saying if less gas gets in here and more goes into the circumgalactic medium, there's less you have to blow out. But what's important as a fuel source is the condensation from the circumgalactic medium. And that is self-regulating very naturally. There's no tuning necessary for some sort of mass loading factor for people know how this goes. And a paper that I will recommend to you. Yeah, there's a simple calculation you can do to say we apply this threshold. We can calculate what the natural rate is of gas going into the galaxy. And a very interesting effect comes in, which I call abundant saturation. If you ask, how is the metallicity regulated? If you enrich the gas, in the circumgalactic medium. You make this bigger, and you push down the rate at which it can condense, because feedback keeps pushing it to a lower density. The only way to get the metallicity to go down is to accrete pristine gas cosmologically. And this thing then tunes to make those ratios, well, make these things cancel, which ties the star formation rate to the inflow velocity at a efficiency that depends only on the depth of the potential. Okay? And I've rushed through that. And the paper I'll point you to is this one from Abject Letters in 2015, where with that simple prescription, there are a bunch of scaling relations that come out that are like real galaxies. This is also known as the Tully-Fish relation, stellar mass metallicity, and the M sigma relation too. And I'm thinking I got 0 time. And I will, yes, just point out that, the key to really testing this further is going to be observations of the circumgalactic medium, whether or not it's in a multi-phase state, whether you see phase transitions happening, but also the kinematics, because as people learn more about the circumgalactic medium, they expected to find cold streams and strong winds, but it is looking closer to hydrostatic, I would say, than people expected. But it's hydrostatic and multi-phase, and I think we should be going more in this direction or thinking about how it works. And so I'll stop there.